In the second video, we will talk about the gravitational fields, Earth gravitational field, Moon's gravitational field, and the influence, the mutual influence that the planet, both bodies, celestial bodies, make on each other. We will talk about the gravity gradient and its influence on Earth rotation. What we mean about gravity gradient? We have to keep in mind the idea that as Moon is pulling the waters, ocean waters in the Earth, it causes the tides. But at the same time, the solid part of the Earth stretches as well a little bit, and this stretching it's favor in the direction of the moon. So when Earth stretches, this stretch is not homogeneous. It favors the direction of the moon, and it makes all the difference because the center of mass, does not coincide with the center of the planet. And it makes all the difference. It is the cause for many things we will see from now on. We put here another picture and we indicate the site because in the site you can find a video that is connected to our conversation, and we recommend this video for you. Earth dislocates a delta mass or region, establishing a gravity gradient. Here we have two pictures in the left. We see that Sun and Moon, both they have their gravitational field, and then they are adding to form the high tides on Earth. So the tides, in this situation, the tides are stronger than when we compare to the right situation, the situation on the right. But as we can see, the influence of the gravitational field of the moon for the formation of the tides is stronger than that influence that comes from the sun. That's why we are considering this binary system, Earth and Moon, and taking the sun for the other time. Analyzing the binary system, we might expect the situation A. In the situation A, we see that there is a line and everything is aligned. Both centers, the center of the Earth and Moon center, and the maximum of the tides are in the same line. But why we have the situation B instead? In the situation B, uh, the line that connects the maximum of the tides and the center of the Earth, this line does not go to the center of the moon. It works as if the Earth was rotating ahead of the moon. And actually, that is what is happening. Considering the angular velocity, Moon's orbit is slower than the Earth's rotation. To be more precise, 29.3 times slower when we take the sidereal month, or 29.5 times slower when we take the synodic months as a reference. The difference is that sidereal months, we consider the stars as the reference for the orbit of the moon, and the synodic month, when we take the synodic months, we consider the sun as the reference for the orbit, for the entire orbit of the moon. And our picture here is exaggerating. As Earth is rotating faster than the moon is orbiting the Earth, it makes the tides, this line that connects the tides, the maximum of the tides in the center of the Earth, ahead of the moon. A little bit, but we exaggerate just to make it more clear. And here we can see, because of that, the force, the gravitational force represented here by this vector in red, does not go to the center of the Earth, but it deviates a little bit. And it causes some interesting phenomena here. While most of the gravitational force acts as a centripetal force, a small part accelerates the moon's orbital speed. As we can see again, the vector that represents the force, gravitational force between um, Earth and the moon, and as moon senses it, and because it's not in the line of the two centers, we can put here a component of this force in the direction of moon's tangential speed, which means that this speed is accelerating all the time. Because all the time, this line that connects the maximum of the tides is ahead of the moon, because what we explained uh, before. So let's see here the other component. The other component is works as centripetal force. This green. This is much greater than this component here. This is the force that um, maintained the orbit of the moon. On the other side, we are talking now about Earth. We have this reaction. For each action, we have the reaction, third Newton's law. And this reaction is a force in the direction of the tangential velocity on the equator. So what this force does is the reaction is in the direction of the tangential velocity on the equator, and it makes this velocity it decelerated this velocity. It has a negative acceleration. So when we are the cause it causes the lengthening of the day on Earth. That's the thing. So here we see that this deviation of the tides, the maximum of the tides, and it makes a deviation in the mass of the Earth, and then it causes the acceleration of the tangential velocity of the moon in its orbit around the Earth, and at the same time, it causes the deceleration of Earth's rotation, which means it's lengthening the day. Moon is distancing and Earth's day is lengthening. Why is Moon distancing? Because each time its velocity increases, it goes further away from the Earth. And the rate is very, very small, 3.75 centimeters per year. And the lengthening of the day, the rate of the lengthening of the day on Earth is very, very, very small, 0.002 seconds per century, which means 2 milliseconds per century. However, we have a detail that cannot be ignored. In the beginning, the moon was much closer to Earth. The distance was between 22,000 to 30,000 kilometers. Let's take it as a 23,000 kilometers, and today it is 384,400 kilometers. When we compare those two distances, the distance in the beginning and the distance today, Moon is 16.7 times more distance today than in the beginning, in its formation. And so the attraction between Moon and Earth was 279 times greater than the current measure. And we go to this 279, if we take this 16.7, the square of the 16.7 is 278.89. So we put 279. Why? Because of the universal gravitational force. It's Newton's law. And it states that the force between two bodies, M1 and M2, Earth and Moon, for example, is inversely proportional to the square of the distance between them. So if the Moon was 16.7 times closer to Earth comparing to today, the attraction was this number, the square of this number, the force of gravitational force was 279 times stronger than it is today. But let's forget it. Let's forget it for a while. And let's think if the acceleration of Earth's rotation was constant since 4.5 billion years ago, the time where the moon was formed. And the phenomenon would have added to the day. If the rate was this one here, uh, 2 times 10 to power minus 3 seconds per century. But we have to multiply for 10 times minus 2 because we are not talking about centuries, but we are talking about years. And 4.5 times 10 to the power 9 because it's the number of the years since the formation of the moon. So if we multiply the rate, the increasing of the day uh, for the increasing of the day per year uh, times the number of years, we get 9.0 times 10 to the power of 4 seconds, which means 90,000 seconds. However, the current day has 8.6 times 10 to the power of 4 seconds, or 86,000 seconds. So it is crazy, it's impossible. If since the beginning this phenomenon had added 90,000 seconds to the day, it would mean that the Earth in the beginning was rotating faster and faster and faster, many times, several times each second, which would be impossible because the Earth would explode. So those numbers don't match at all. And remember, we just forget that in the beginning, the relationship between Moon and Earth was much stronger. Here we put it on the graph. This would be the graph if the deceleration rate of the Earth rotation were uniform and equal to 2 milliseconds per century. Uh, Actually, we didn't go to this red line until the moon's formation. And we will talk about this later in the next video, as if this rate was started after 1 billion years after the moon's formation. What difference it makes when one seriously take in consideration the distance between Earth and Moon in the beginning? Let's put on the table what we've talked about minutes ago. So this is the thing. Because Earth and Moon was very close comparing to today, so the force, the gravitational force that was among them was between them was very strong. And then as times went on, this rate, considering seconds uh, times the 10 to the power of minus 3 per century, this rate was this high, and then it decelerated, this went down until today. The rate today is 2 milliseconds per century. So that would be the graph, the actual graph. And we have to calculate the area below this line to have the amount of time that was added to the day since the formation of the moon. And again, we put this graph starting 1 billion years after the formation of the moon. So this is the function that is connected to this graph, and we will go into details and analyze in this graph the next video.